What we have done so far is to discuss how we can evaluate the truth of a formula relative to a single valuation. So we have a formula phi of any arbitrary complexity and a valuation v, so a single valuation v. When the valuation v makes true the formula phi, we write this expression. So remember that the symbol with this vertical bar and the two horizontal bars means makes true. The valuation v makes true the formula phi. The next step is to evaluate a formula relative to more than one valuation, and actually relative to all the possible valuation. This is the topic of this video. It's important to keep in mind that there are more than one possible valuation functions. And you might ask, how many valuation functions are there? We've seen this before in another video, but just to refresh your memory, the number of valuation functions that are there depends on the number of atomic propositions that we are considering. So for example, if we are considering only one atomic proposition, then there are in total two possible valuation functions. One is the valuation function that assigns the truth value true, or 1, to the atomic proposition in question, and the other is the valuation function that assigns the truth value 0 or false to the atomic proposition in question. If we have two atomic propositions, then there are in total 4 possible valuation functions. If there are 3 atomic propositions we are considering, there are in total 2 at the power of n, namely 8 possible valuation functions, and generalizing this, if we have n atomic propositions, there are in total 2 at the power of n possible valuation functions. So the task now is to evaluate a formula relative to all the possible valuation functions. So let's consider an example. The example here is the formula P, and P implies Q implies Q. So this formula has two atomic propositions, P right here, which is repeated here as well, and Q, which is repeated here as well. So since we have two atomic propositions, there are in total 4 possible valuation functions, and those are listed here. So according to the first valuation function, we assign value 1 to both P and Q. According to the second valuation function, we assign the value 1 to P, but we assign the value 0 to Q. Then, according to the third valuation function, we assign the value 0 to P and the value 1 to Q. And finally, the fourth valuation function is such that we assign 0 to both P and Q. So these are all the possible valuation functions relative to the two atomic propositions, which are the only atomic proposition that constitutes this formula. Once we have listed all the possible valuation functions and assigned all the possible truth value to the atomic propositions, the next step is to evaluate the truth value to the more complex formulas. And we can start here with the formula P implies Q. And these are all the possible truth value that we can assign to this formula. Why is that? Well, this just follows from the truth table for the implication right here. So if both antecedent and consequent, namely P and Q, have truth value 1, then the implication also has truth value 1. However, if the antecedent has truth value 1 and the consequent has truth value 0, we know that the implication will have truth value 0. Then in the remaining two cases, since the antecedent has truth value 0, then the implication will have always truth value 1, regardless of the truth value of the consequent. The next step is to evaluate the truth value of a formula that is slightly more complex than P implies Q. And this is the formula P and P implies Q. These are the truth value of this formula. So they're listed right here. This formula is the conjunction of P and the implication P implies Q. It is easy to check that this truth value of the conjunction follow the truth table for the conjunction. If P is assigned truth value 1 and P implies Q is assigned truth value 1, then the conjunction has truth value 1. If P is assigned truth value 1 and P implies Q is assigned truth value 0, then their conjunction will have truth value 0. If P is assigned truth value 0 and P implies Q is assigned truth value 1, then their conjunction will have truth value 0. And finally, if P is assigned truth value 0 and P implies Q is assigned truth value 1, then their conjunction will have truth value 0. Finally, the next and final step is to assign a truth value to the formula that we are interested in, which is the most complex formula here. This is the formula P and P implies Q implies Q. And the truth value of this formula are listed here. What you see is that this formula always has truth value 1 in every possible situation. Is this the case? We can check that. So this formula is an implication, so has the structure of an implication. This is the antecedent of the implication, and this is the consequent of the implication. So Q is the consequent of the implication, and P and P implies Q is the antecedent of the implication. So we need to consider the value of the antecedent. So if the antecedent is assigned truth value 1 and the consequent Q is assigned truth value 1, then we know that the implication has truth value 1. This follows from the truth table of the implication. If the antecedent is assigned truth value 0 and the consequent is assigned truth value 0, then the implication as a whole again has truth value 0. Now you see that in all the remaining cases, the antecedent is assigned truth value 0, and therefore the implication as a whole is assigned again truth value 1 in every single case, because whenever the antecedent has truth value 0, then the truth value of the implication is 1, regardless of the truth value of the consequent. So this is an example of a formula that is always true no matter what kind of valuation we consider. Or in other words, the formula here is true relative to all possible valuations. Below here, instead, you see a formula that is true only relative to some valuation and false relative to other valuations. So this is the formula not P. It's a double negation of P. So there are two possible valuations here, the valuation that assigns 1 to P and 0 to P. Now if we consider the first valuation, the one that assigns 1 to P, then the truth value of not P is 1. And this follows from the truth table for the negation. We know that negation inverts the truth value. So if P have truth value 1, then not P will have truth value 0, and not P will have again truth value 1. If we consider the second valuation, namely the one that assigns 0 to P, then the truth value of not P will again be 0. And this follows from the truth table for the negation. If P have truth value 0, then not P will have truth value 1, and not P will again have truth value 0. So not P is a formula that is true relative to one valuation, but false relative to another valuation. To conclude, it's worth making a taxonomy of the different types of formulas. Some formulas are never true. These are known as contradictions. So an example is P and not P. This is a contradiction when you say P and then you say not P. If you write down the truth table for this formula, you will discover that relative to all valuation, this formula will always have truth value 0. So formulas that are never true, formulas that always have truth value 0, no matter the valuation you consider, are known as contradictions. Then there are formulas that can be true. So they are sometimes true and sometimes false. The example we saw before was not P. Another example you see here, not P or Q. This is sometimes true and sometimes false, depending on the valuation. And then there are formulas that are always true. And we saw the example of P and P implies Q. This is always true. Such formulas are called tautologies or valid formulas. Whenever a formula is valid, we write this way. So we use the symbol with the vertical bar and the two horizontal bar, and then we write the formula in question. This means that the formula is valid, or in other words, that the formula is always true, no matter the valuation we consider. Now, just as a matter of notation, so remember, we write V makes true phi to indicate when a formula phi is true relative to one valuation, and the expression makes true phi without the specification of the valuation relative to which the formula is true means that the formula is true relative to all valuations.